Okay, this is my Game 2005 Assignment 1 for Sarah Gowdy. We start with the first test launch being held at the moon at an angle elevation of 20 degrees from the horizon. At the test site, acceleration due to gravity is 1.6 per meter squared downward, and there is no air resistance. Our variables include our initial velocity of 120 meters per second and our gravity acceleration of 1.6 meters per second squared. We can calculate our expected launch velocity of x and y by first calculating our x equals initial velocity cosine theta, and then our y, which equals our initial velocity sine n theta, which finds 112.76 meters per second and 41.04 meters per second as our vector. These are also our equations for the next question. If we were to graph this, this is what our launch would look like, roughly, in 2 dimensions. To determine where the package would touch the ground or our final position, we would use the formula final position equals initial position plus initial velocity, delta time, plus half of acceleration, delta time squared. Assuming p equals 0, we rearrange and we get delta time equals 41.04 meters per second divided by 0.8, leaving us with the time of 51.3 seconds. Plugging the time back into the formula, we can calculate that the final position is 5,784.59 meters. If the angle was 70 instead of 20, the distance is actually the exact same with a final position of 5,784.59 meters. This is because x and y are proportional to one another, and we can see this as either a steep or shallow trajectory. The alternate angle can be found by taking 90 degrees minus theta as the elevation. To create a formula that generates elevation angle solutions for any range, we can use r equals initial velocity squared times the square of sine theta divided by gravity. Rearranged, we get theta half of the inverse of sine r times g divided by the initial velocity squared. Note that this only works for our problem because we have zero air resistance. With theta representing our launch angle, we find this by using range times gravity divided by initial velocity squared, which represents the ratio between the gravitational force and the kinetic energy of the projectile, which influences how far it can travel horizontally. Using this formula, we can plug in specific ranges and determine the elevation angle needed to reach them. You'll notice that at 9,000 meters and an angle of 45 degrees has no alternate because 90 degrees minus 45 is still 45. You'll also notice that at the 10,000 meter does not have any elevation values because no matter the elevation, the package maxes out its range at the 45 degrees and 9,000 meter mark. And that's everything. Thanks for watching.